Oh hi, do you like planets? I do like planets. I just love space in general. It's peaceful yet chaotic, dark yet bright, infinite yet limited, but most importantly, it's extremely large, at scales where you really cannot tell a normal game engine to draw a real scale planet. Or can you? I am currently sitting in one of my many abandoned projects. Abandoned because, well, it's too hard to do things alone. But despite that, I have achieved the main goal of my project, which is surpassing the limits of rendering. The planet behind me is Venus. Although it's portrayed as an orange-yellow planet, its surface is covered by sulfuric acid clouds, which makes it look white from the outside. But then, how could you bring space objects to real scale without having to increase your far plane distance to insane numbers? If you saw my first scripted video about ray tracing and path tracing, you may know where I'm going with that. This planet is raycasted or ray traced, whatever you choose to name. But there's more to this trick than you may imagine. So let me show you how you can do this for yourself. Let's create a new unlaid shader and remove all the lines related to fog rendering, plus the fragment shaders. Then make it return 0 to avoid compilation errors. In this shader, you will use a CG include. You have to write it before the pass and end with ncg. This command takes what's written inside of it and clones it inside of every pass inside the shader. Inside the CG include, create a structure for the ray. We will need the position, normal, depth identifier, and the hit indicator. We will also use the vertex structures and shader in here since we will use the same for all the passes. The vertex input will only have the vertex position. The vertex to fragment output will have the clip position and the build direction. On the vertex shader, the clip position will be the usual one, and the build direction will be the wall space camera path minus the multiplication between unity object world and the vertex position. Then write the ray sphere intersection function. Input the ray origin, ray direction, sphere position, radius identifier, and the current ray as an input-output parameter. If you don't remember the base formula, it's this. You get the position between the sphere and the origin, get the square distance of the direction and that position, and then the square distance of just the position, minus the square radius of the sphere. Get the shape as the first distance multiplied by itself, subtracted by the second distance. And if that shape is higher than 0, keep calculating. After that, the depth will be minus the first distance minus the square root of the shape. If that depth is higher than 0, you intersect it. We will add a condition, which is if the ray depth is lower than 0, or if the intersection depth is lower than the ray depth, you intersect it. After this, you can write the ray data. The position is the origin plus direction multiplied by the depth. The normal is that position minus the sphere position normalized. The depth is the one we calculated previously. The identifier is what we input into the function, and we will indicate that we hit a shape. Now, when I worked on my project, I found a problem. Planets are millions and millions of meters away from each other. That will really mess up the position. And then I found a solution. Shader Model 5 supports double floats, which are 64-bit floats with a much higher precision and mantissa limits. Little did I know, this would become a disastrous error. I learned something, and you will learn it now. Do not use doubles. No excuses. Use floats whenever you can. There's a page where you can compare various graphics cards, and guess what? 32! Most consumer-level graphics cards run 32 times slower with double floats than single floats. Unless your game is targeted towards professional graphics cards users with Quadro and Tesla GPUs, do not use doubles. So yeah, then double floats were not an option on my GPU, but they are on my CPU. It might sound absurd, but you can even use decimals on your CPU, which are 128-bit floats, which is insane. But for now I'm good with doubles, which seems to be what Unity works with by default, since it always cries like a baby if I don't put an F next to a number. So then my plan became, I will have a script with an array of doubles indicating the distance of each planet from its center of orbit, which would be nearly at the center of the Sun, and also an array of the same scale for the respective planet's radius, plus another one for the atmosphere thickness. And then I'd have a set of 3 doubles to indicate my position. Every update I would create a vector tree array for all the planets. Then for every planet, I will get its position on another set of 3 doubles, subtract that by the current position in space, convert this to a vector tree, assign it to the array. Once finished, I will send this vector array and the arrays containing the planet and atmosphere radius to the shader, and also an integer with the number of planets we have to render, which is the length of the position array. Now I have a precise position, and I don't need to use doubles on my shader nor lose position when calculating my position from the planet. The way you display the space position is up to you. My map uses a steering wheel system to drive the ship, which is practical to move around, but in some cases it takes me nearly half an hour to go from one planet to another. Now we're going to do another trick. Although sphere intersections are not that expensive to render, I always prefer to keep my rendering costs minimal. And although conditions can now be correctly handled by a pixel on modern GPUs, not all GPUs are modern. Not with these prices. So before rendering the planets, we're going to mask them. We will also clone the paths twice. The first one will be the mask, the other one will be the background, and the last one will be the planets. First we will do a stencil pass. It will always write a value. It can be any number. Since it's a stencil only pass, its color mask will be 0, so it won't write RGB nor alpha colors. We will use a modified sphere intersection formula, which only receives the ray origin, direction, sphere radius and position, and it returns a boolean to indicate if it has intersected. Leave only the base calculations, and only return true if it intersected, otherwise it will return false. Go to the fragment shader, normalize the view direction and create a boolean. The ray origin will be underscore ball space camera pass, and the ray origin will be the negative view direction. On a for loop, iterate for every planet using the previous function. If it intersected from the ray origin towards the ray direction at the current planet position with its current radius plus atmosphere thickness, the boolean will be true. After the loop, if that boolean is false, discard the pixels, and in case it didn't get discarded, return 0. You could also make the shader not return any value, but I didn't have good experiences doing so with AMD GPUs. Now on the next pass we will render the sky. Using a stencil, it will render only if its value is not equal to the one we wrote before. To make it blend correctly, the sky will be separated on a function inside the CG include. Its input will be the ray origin and direction, and its output will be a float tree color. To sample the stars, I will go to Blender, set a mask scrape texture for the skybox, and using an equirectangular camera, I will render a cube map for the star and noise. This will be a unique texture, so don't worry if it's 2K or 4K. On the import options, set its type to cube, disable map maps, set its resolution to have the lowest resolution, and set its compression to high quality. Add a cube map texture property on your shader, declare it on the decision include, and sample it on the right direction. It obviously does not look in any way like a bunch of stars, but that's where you use the power of the power. Raise this texture to whatever power you prefer. To change the amount of stars, multiply it by a higher or lower value before being raised. Make sure to clamp it afterwards, because if the values are higher than 1 and the exponent is very high, it will cause such flashes if you add bloom to the map. Like, look at this, who even made that? Of course, add whatever you please to the function, the stars are just the base. Once you're done, go to the fragment shader, sample the sky on a float tree, and return it as a float 4 with the alpha being 1. This pass is finished. Now the next pass will do a stencil that will render if its value is equal to the one we wrote on the first pass, so the pixels where the planets are present. Just as we did before, sample the sky on a float tree, and now we're ready to draw big balls. Create a ray and on a for loop, trace all the planets again using the normal ray sphere function. To check if it works, you can return any of the ray's parameters in play mode. Unfortunately, if you didn't know, the planets are clearly not the size in which they are portrayed in articles. Why? Well, look at this image. Yeah, look at this image, it's the whole solar system. If the planets were really at such distances, all of them would have been obliterated by the sun already. To get a more comprehensive perspective of the solar system, go check out this video showing a sculpture that brings a replica of the solar system to Earth. Anyways, if you reduce the planet distance by about 100 or 1000 times, you will get a better view of them together. You can keep it like that until you are finished with the shader, then send it back to the original distance. We will keep rendering the planets if the ray hit a surface. The first step we're going to do is calculate the lighting. Since barely any light other than the sun's radiates on these planets, we only need a single dot product. We have to calculate the location of the sun. We will have it on the shader as a float tree. Its location is calculated the same way as the planets. Its position minus your position. It could be 0 minus your position since the sun is where the planets orbit around, although in reality there's a slight pull that makes its center of gravity shift, but is anyone ever going to care? So you assign the sun's position on the material as a vector tree and now go back to the shader. Now what you need to do is get the sun's direction. Typically this will be the normalized wall position of the ray minus the light position. What you have to do now is get the saturated dot product between the wall normal and that direction. In some cases you might want a more accurate dot product for planets that are closer to the sun. You can give a size to the light by adding the dot product by the light radius divided by the distance between the wall position and the light position. This is the basic lighting of the planet. After this you can start sampling the color of the surface, likely on the UV coordinates. This is the thing, there are no UV coordinates on sphere intersections, so you have to build them yourself. The x-axis is the two-value arctangent between the normal's x and z-axis, and the y-axis is the normal's y-axis multiplied then summed by 0.5. Now we can sample the planet color. Let's do it on a separate function, with its input being the UV coordinates and the ray identifier, and its output being a float tree. In here you're free to do whatever you want with it. In my case, I will add a texture array containing all the planets in their respective identifier order. These textures are free and you can get them from this website. You can find the link in the description. I just mashed them together in Blender, and in the import settings I set it as an array with its respective rows and columns. And then I sampled the texture with the index being the ray identifier. The results of the planet's surface is the color we sampled multiplied by the light dot product, and maybe the sun's color, but technically it's white. The reason it appears yellowish is because higher frequencies, which are a bit of red, a part of green, and mostly blue, get scattered on the atmosphere, spreading around the sun and so becoming less intense than lower frequencies. Of course this varies depending on things like the pressure and thickness, other stuff that I have no idea about. Talking about atmospheres, adding an atmosphere to the planet is a bit tricky. Most people do a physically based atmosphere for the sake of realism and because in some cases you might want to enter the planet's surface. Gladly, you can approximate this however you prefer. Since we will render this outside of the planet's boundaries, we're going to leave this prison of conditions and doubts. Create a new function to render the atmosphere color. It inputs the ray origin, direction, planet position and radius, atmosphere radius and atmosphere scattering and decay, and it outputs a float tree. On another loop, iterate for every planet, and every time if the thickness of the atmosphere is higher than 0, sum the result by the atmosphere with its respective parameters. The approximate function to render an atmosphere starts with another sphere intersection. Yes, it's the third one already, I know. I based this function on this article made by Emil Jabanowski, so big credits to him because I was about to explain my less convincing formula at this point. This time the intersection will not be skipped if the sphere shape is not higher than 0. The depth will be the same, but the shape gradient will have a maximum value of 0. You will see why now. The wall position on normal is calculated as usual. You can see that since the shape gradient doesn't have a negative values now, the normal and position extend outside of the sphere's bounds. This will be necessary now to get the dot product between the sun direction and normal. Like before, it will be the dot product between the normalized light position minus wall position and the wall normal. Now we have to get the atmosphere's density. First, we will normalize the shape gradient by dividing it by the squared radius of the planet. If the shape is lower than 0, this gradient will be turned back to linear by getting the square root of 1 minus itself. It will be subtracted by 1 and multiplied by the radius, and it will be divided by the atmosphere's thickness. On the opposite side of the condition, the gradient will be the square root of itself multiplied by 0.5. After the condition, raise 1 minus the gradient to the power of 5, because for now it's so cool. The result of the atmosphere is light dot product shifted by the scattering. After saturating it, raise it to the power of the decay. This simulates the light radiation scattering more or less depending on its frequency as I mentioned before. Lastly, multiply that by the atmosphere gradient and return it. This is a fancy atmosphere, right? Again, thanks to Emil Jabanowski for helping me discover this function with this article. You can have the scattering and decay inside the shader as two static float tree arrays, or set them by the script we wrote as two arrays of vector tree. Mercury doesn't have a visible atmosphere, so we can skip it. Venus's atmosphere conditions make it so light frequencies are scattered evenly, which leaves only the planet's surface tinted with a yellowish-white color. The scattering will remain untouched. Then the decay will be 2 in red, 3 in green, and 4 in blue. Earth's atmosphere scatters green and blue light more than red. You can notice it by seeing how the sky fades from a bluish color to cyan to a yellowish white. Do not do that with the naked eye. So the scattering will be minus 0.3 on red, 0 on green, and 0.3 on blue. The decay will then be 5 in red, 3 in green, and 2 in blue. Mars's atmosphere is not as dense as Venus's and Earth's. It is said that it has a rusty tan color, which means red light gets scattered a lot, but is also dim, while green light is barely noticeable and blue light is basically gone. So my approximation for the scattering will be 0, minus 0.2 and minus 1 respectively, and the decay will be 2, 4 and 1 because there's no blue light to add decay to. Although these are not physically accurate, you saved a lot of calculations with this. Gas giants are made of a very large layer of gas. So technically the atmosphere is the only thing you can see from the surface, making it so overlaying a fake atmosphere over it won't be necessary. So the atmosphere thickness of the remaining planets will be 0. Now, the last thing you need to do is to add the Sun. I totally didn't forget to mention it before. Add a new value to every array. The Sun's distance from the center of gravity is going to be 0, because I say so. Its radius is going to be its radius, and it won't have an atmosphere because it's just an angry ball of plasma. Keep in mind its index in the array. In the part of the fragment shader where we draw the planet color, we will add a condition where if the identifier of the ray is equal to the sun's, the color will be big number. I apologize for not being an astronomer, but yeah, that's our goal. Our goal here is to make convincing graphics. Physically accurate calculations are very expensive for real-time graphics, and I believe we have enough with the current state of avatar shaders. May the Lord have mercy on my frames. But yeah, large color. The sun is so bright that even without an atmosphere there's glare, which is the reason why bloom is there. Please stop using low threshold bloom. Yeah, that's everything. Before vanishing into a next up screen, I want to thank every one of you for watching this video and everyone who subscribed and support my content. It means a lot to me. So yeah, join my Discord. Okay, bye.